feed.
Oh, great. So thanks again for inviting me to give this talk in this very interesting and exciting session at the World Microwave Congress. I would like to, first of all, I think it's a very nice introduction that Soya gave, and I would like to complement that perhaps a little bit from the perspective of our university and perhaps Europe and Sweden specifically. But first, to let everyone know a little bit more about where Chalmers University is located. So we're up north in Europe. We don't have ice bears on the streets. On the contrary, we have a very beautiful nature up here. And these pictures are, the right one is just from outside of my garden where I live. Our university was founded in 1829 by William Chalmers, and we have around 10,000 students and 3,000 employees. And the employees here, it's perhaps important to note that those are mainly PhD students, because we have our PhD students as employees with all the benefits of an employment like vacation and pension rights and everything. When it comes to microwaves, we have a rather long tradition, which actually started around radio astronomy. So much of the research was for a long time about receivers for radio astronomy, but since then things have evolved quite a lot. So we have actually quite a large number of researchers and professors at Chalmers doing microwave and terahertz research and education. I think we're around 100 active researchers, teachers, and PhD students who do all kinds of research in this area. If I should point out a few of the key directions that we focus on, I can mention wide bandgap technology, which I will come back to a little bit later. The same for telecom transceivers, which myself I've been doing quite a lot of research in, but we also have a very big activity on terahertz components, circuits and systems by Jan Stake here. Mariana Ivashina is leading the research on antenna systems. We have radio astronomy and quantum computer receivers. That's also a very important field with several groups, for example, Vincent and Jan Gran, for example. And recently we also had a group on VLSI system design joining us. It's a bit interesting because they actually worked in a computer science division before, but since they were doing hardware, they didn't really feel that they fit because it moved more and more towards AI and the software where they stayed. So they felt that they have much more belonging to us working on CMOS circuits and hardware. So we're very happy to have this group joining, and we see a lot of synergies happening. Around this, we have two master programs, one in wireless photonics in space and one on embedded electronic systems engineering, with roughly around 50-60 students per year in total. So I also talked a bit about the need and importance of infrastructures. And we're also very happy about the infrastructures that we have at Chalmers. And in some respects, they are really world class. We have a clean room, which we call the nanofabrication lab, around 1,240 square meters in different classes. So this is where much of the research on the component level is happening. We have a very comprehensive RF and terahertz lab facility or infrastructure covering continuously from DC to 1.5 terahertz with all kinds of instrumentation. We also have an antenna lab, as I mentioned. Mariana Ivashina is having several anechoic chambers and also reverberation chambers for doing measurements on antennas and antenna systems. And on top of that, we also have a radio observatory, which is located outside of the city in a couple of kilometers away. So this is the infrastructure, which is very important for us. And I should say that one thing is that we have all these infrastructures are shared. So doesn't belong to any specific professor. We share the labs, and we fund it by common funds, and we apply for joint funds to support these infrastructures, paying lab fees, etc., when we use them. One thing that we also like Soya was into is that we see it very important to collaborate with industry, because we think that industry not only helps us in indicating areas of interest, but it also gives us, for example, employment to the students that we educate, but also helps us in many cases with direct funding of the research. We have several centers and collaboration centers, and we have very long history of collaborating with industry in Chalmers. A newly started center called WireTech, which is on wireless infrastructure technology with a large number of companies. A center called CNIT, which is focusing on gallium nitride technology with Lund and Uppsala University. And Classic Center, which is also a new center focusing on semiconductor system design with a quite strong focus on CMOS. So I think this somehow sets the scene for the research that we do. And then the question is, what are the main directions that what are the driving forces in our research? Well, from the application point of view, here we have an overview of, for example, some of the typical applications. We may have, let's say, 6G or virtual reality will drive one type of research. We have Earth observation, also driving research in many aspects. Non-terrestrial networks, automotive sensing and joint sensing and communication, for example. Quantum computing, I think that's also a very important and growing field. Radio astronomy, already mentioned, and defense. But if I should bring this down to some specific topics, then I think energy efficiency goes like a bottom line topic that connects all of those things together. Secondly, capacity and security, but I think energy efficiency is really important. And to do that, we really need to look at the problem in a multidisciplinary way. Not only looking at the individual, for example, semiconductors, circuits, and algorithms, but really looking at it from a multidisciplinary perspective. So that's a little bit what I will give an introduction to some of the research directions that we do now. So the directions, if I should start in one direction, we work on semiconductor research, Niklas Ruschmann. We have actually an in-house full MMIC process, going all the way from MBE, material growth, process development, TCAD. We do device processing, we do modeling of the devices, and we build circuits. So I think this is really, in one sense, unique in Europe to have all of that in a university lab. So we collaborate strongly with the semiconductor suppliers to do this. And recently, we're also very happy to see that we were selected as partner in one of the pilot lines that are now being launched in the European Chips Act. So I think that's really something I would like to highlight. Another direction is that Soya also was into before is obviously efficient amplifiers. And efficiency here means reduced energy consumption, but in many applications, it's also the heat that we want to minimize, or, for example, the weight. And we already were introduced to this before. And looking back, it boils down to understanding the trade-offs between different parameters and pushing the limits. So we have pushed efficiency limits over the years. We have investigated new architectures. We have studied multiband architectures. We've looked at extremely wideband circuits, integrated different technologies, and also pushed the frequency limits. So that's the broad terms. But if I should give some just recent examples on the next slide. Here's an example of some of the ongoing research where actually in contrast to the overt amplifier, we're using a circulator to act as a combiner. I think this is in one sense very counterintuitive. When I saw this the first time, I thought this looks exactly like a low pull system, active low pull system, but actually it can also act as an efficient amplifier architecture. Not perhaps the most, let's say, useful, but I think it's very interesting from a theoretical and understanding point of view to look into new architectures. And it turns out that the performance is actually very good. Another thing that is fun is to not have a circuit combiner, but actually use an antenna element as a combiner. This is not something that we started to look at, but I think it's also a very interesting direction for the future to see how antennas, circuits can work together to realize a transmitting function. And again, the performance that you can get here is really remarkable. All right, so that's just some examples of things we look at for the moment. Another direction that we were into is on CMOS. We look into use of CMOS technology for transmitters. And here it comes down to integration of circuit functions, analog circuit functions like mixers, amplifiers, etc., with D-to-A converters, memories, and digital processing functions on the same chip. So here's an example of recent work by Victor. So we achieve very high sampling rates from a single chip, and more than 11 gigasamples per second. And I think this really is an enabling technology for going up in frequency and building highly integrated millimeter wave active antennas. So that's one example of research that we are going into. Another interesting area that we worked on for a very long time is linearization, because circuits is one thing, but we also need to co-design them with the algorithms. And here we look, for example, on how can we find the best trade-off between linearization performance and computing complexity. So that's a very interesting research area. And of course, also multi-antenna linearization problem is also another very important area that is open for a lot of new research. I also would like to mention here the facility that we have. We have actually an RF Web Lab, which is an open access DPD lab that any of you can use. It's actually openly available. So if you scan this QR code, or if you go to RF Web Lab, if you Google RF Web Lab, you can directly download MATLAB code to run an experiment with DPD yourself. And for the moment, it has been used more than 1 million times from all over the world. I think this is really interesting for many of you. Linearization and the circuits is one thing, but looking at it one level above, it's interesting to also look at the modeling and understanding how circuits behave in an array. So we have done quite some work on integrating power amplifier modeling, antenna modeling, and the thermal modeling, because the thermal effects are actually turning out to be very important in these systems. So we worked on equivalent thermal circuit modeling from multiphysics simulations, combined with circuit models and antenna models in predicting all kinds of properties like beamforming, the load dependency effects that Soya talked about, and stuff like that. And I think this is really something that I think is very important and fun to work on, and has many open areas for research in the future. But this is, let's say, on the circuit array modeling side. If you take it one step further, we have also a quite big interest in the evolution of wireless communication systems and actually sensor systems as well. There's a big trend now from co-located systems towards distributed multi-antenna systems. So if we take a 5G base station as an example, I mean, we have co-located multi-massive MIMO unit. The problem occurs that still there is a lot of correlation between all these different channels. So if we could look at a more distributed antenna system, we could get much better properties and uniformity of service. It also turns out that the efficiency will be much better because the distance in average from the user to the access point is reduced. So the problem here is that how do you realize such a system? How do you distribute the signals? What will be the performance with real hardware, and how do you maintain coherence to do beamforming from all these different transmitters? So actually, that means that we need to build some hardware and we need to do tests. So that's something we have been doing. We have been working on test beds for distributed antenna systems. And here we have utilized off-the-shelf commercial components to build a really low complex and simple to use test bed for this. So here is how version 1 looks. It has an FPGA, and we use actually all digital radio with fiber technology to distribute RF signals from a central processor to these remote radio heads. And we don't do any frequency conversion at the radio head. Everything is done digitally in the central unit. So we can maintain very good phase coherence and study these communication systems with this test bed. We also built a little measurement robot that follows a line and performs measurements automatically along this line. Using this test bed, we've actually performed measurements in an office environment. So this is our office environment at Chalmers. The measurement has been traveling around, and we compared a centralized antenna deployment to distributed antenna deployment, and collected channel state information and did estimates of capacity. And here to the right, you can actually see how consistently higher the capacity of the distributed antenna deployment is compared to the CMIMO centralized 5G type of communication system. So I think this is also very interesting and something that opens up for a lot of new interesting research in the future. And actually, this can be taken one step further because we can combine this at low frequency with distributed MIMO systems at high frequency, because actually it probably makes even more sense to do this at higher frequencies where the blocking of signals at, for example, L-band is very severe. So we have an example of an EU project here where this is studied. And actually here it's a quite funny project because it brings really together communication theorists, antenna designers, terahertz electronics and measurement people, communications already mentioned, but actually also mechanical engineering people, as we will come into later. And actually, here's an example of a demonstration. So we developed chipsets, or rather Frida and you and Herbert in this team developed these chips. They performed measurements and actually used dielectric waveguides to distribute the signals in the system. They achieved more than 100 gigabit per second, and it's quite remarkable. And here actually, I think it was also very fun because I was allowed to take a quote from Frida here, because I think it reflects very much what I think this is all about. And I think many of us can recognize that there is not really much interest from other people about what we do, perhaps. But as long as you stay curious, then you can do things and have fun. And I think that's really some takeaway message for all of you. From that, I now want to get back a little bit to wrap up and say something about how EU comes into play in this. Because what I described here are some technical directions, but actually, in a larger perspective, everything is about educating people. I mean, I think Soya was already into that. How do we educate people, and how do we make it fun for people to do this kind of research or what we're investigating? So in Europe, there are different initiatives in this direction. For example, one good example is the Marie Curie doctoral networks. And in those networks, we have actually 15 PhD students from different backgrounds joining a multidisciplinary program with a certain target. And actually 18 months of their PhD time they spend by an industrial partner. So they have a joint training program, and we have different focuses of those training programs, those networks. One we had was on millimeter wave arrays. One was on distributed MIMO, and one on terrestrial communication, which is now running. And as you can see, there are lots of industries involved, and it is really, really fun for these PhD students to work on those different companies, getting to know each other, and to spend time in different parts of Europe. So I think this is really a good example of how the European Union can help bringing people together, at least for us. So in summary, I have presented some of the main research directions at Chalmers, also a little bit about the infrastructure and things we have here. I think that the European Union at least promotes international collaboration and exchange in different ways, both through pilot lines, but also through research projects and training networks, as I mentioned below, but there are many other initiatives. But I think the main message is that as long as you stay curious and follow your dreams, then there are lots of opportunities for all of you. So I think that's basically the end of the story for me.